Hi to everyone. Welcome to this channel. This is Chilemat. We are two friends from the north part of Chile, and we hope to solve your doubts about physics and mathematics. So today we are going to solve a quantum mechanics problems, and it reads like this. A hydrogen atom at time t equals 0 is in the state C described by this function where each of these phi's are where phi and Lm denotes, depending on the positions, denotes the eigenstate of the hydrogen atom with energy level En equals to this expression, and L and M are the quantum numbers associated with the angular momentum observables. L squared and Lc respectively. Calculate the probability of measuring Lc equals to the Planck constant or h bar. So we are going to start rewriting these functions over here. C depending on the square root of phi 211 plus 1 over the square root of 3 multiplied times P311 plus 1 over the square root of 6 with 5 depending on 3, 2, 2. So they are saying us that the the subindexes represent a quantum number. So for instance, let's consider these numbers N, L, and M. Here we can notice that we only have two energy levels. So as you can see, N is just 2 and 3. There are only two possibilities, and those are when N is equal 2 and when N is equal 3. So with these considerations, we are going to solve the probability for the condition that they are asking us, that we want to measure the next observable. That the orbital angular momentum needs to be equal to this quantity. So for that, we just need to consider the orbital angular momentum. And if you remember your assignments and your courses, you can take in consideration this formula. There are two formulas. One is something like this: L squared with the ket L with M is equal to h bar squared L times L plus 1 with the ket L and M. Another possibility is that the C angular momentum is with the ket L and M is just h bar M and the ket L comma M. So we need to achieve this consideration that LC is equal to h bar. So the probability associated with that, well, the overall probability over this function will be just something like this, that I'm going to write it over here. And the probability when LC is equal to h bar at a time, and the problem says that it is at a time 0, I think. Yes, time 0. So this term is just 0. With the time will be something like this. the bracket with 2, 1, 1, and the wave function to the square plus the bracket. I'm sorry. This is just the bra P311 with the wave function C and all this to the square. And then why just these two? Oh, oops, sorry. Why only these two probabilities? Because we only have one. We only have one. Two. I'm sorry. We only have two energy levels, so we just need to consider it over here. This is 3, 2, 2. Sorry. For instance, let's remember that the time evolution operator behaves like something like this. That is just an exponential term minus the imaginary term, the energy level, and this is multiplied with the time, right? Divided into h bar. So we just need to, we're not going to use it, but just take in consideration that when we apply this bracket and this bracket with the wave function, we will have this operator at equal times. And in this case, the time is equal to 0. So independently that, we may do something like this, because the bracket in the bra, I'm sorry, we will have the energy level equal to 2, and in this case 3. So for example, in the first case, for instance, will be something like this with the energy level number 2 over h squared. And if you take the conjugate of this term, then you multiply it with this same term, you just will have something like this, that is an exponential term equal elevated to 0, and that is just 1. And this will be for both cases as well for this case. So in this case, just will be minus the imaginary term, the energy level number 3, and when you take the conjugate of this, then you multiply it times this. This will be exactly the above case, equal to 1. So we're not going to use this, but it's just that you need to take it in consideration if you want to solve problems that are not in the at time equals 0, like this problem says. So these considerations makes the problem a bit easier. So we just need to solve it directly using this probability over here. We are going to use this probability. Why is with phi equals 2 and phi, I'm sorry, with phi in the energy level 2 and phi in the energy level 3? Because we only have those degrees of freedom, right? We only have the energy level 2 and the energy level 3. We don't have more. So let's continue with that. For the first case, oh, sorry. For the first case, when n is equal 1, sorry, again, this is just 2. When n is equal to. So in this case, we are going to need to see that N, L, and M are equal to 1, 1, right? So N, L, and M is just 2, 1, 1. Therefore, the associated bracket and the corresponding probability of this will just be the thing that we have here. P2, 1, 1 with the get to the square, and this probability reads like something like this. Will be just this multiplied, I'm sorry, applied to this wave function. And that is just 1 over square root of 2 with the bra 3211, right? The get 1 over the square root of 2 with the get 3211 plus 1 over the square root of 2 multiplied by 1 over the square root of 3, sorry for my English. We are not native speakers. We are from Chile, so we are trying our best. And 211, P311 plus 1 over the square root of 2 multiplied by 1 over the square root of 6, and this with the bra P211 and the get P322. Let's observe that these terms are equals to 0. Yes, this is a multiplication. This term is 0, this term is 0 because they are not orthogonal, and these have the same quantum numbers. So this probability is just 1 over the square root of 2 multiplied by 1 with the square root of 2, and this and this bra, this bra is just this bra, this bra is just 1. This is equal to 1. So I'm going to write it over here, 1. And this is just the square root of 4. That is 1/2. Right? So again, I'm not writing the time evolution operators because you may notice that at equal times and at equal energy levels, it is just 1, the exponential term. So let's continue with the calculations. Now when the energy level is equal to 3, when n is equal to 3. In this case, we're going to have the next expression. The bracket with P311 and the wave function C squared. This will be just 1 over the square root of 3 and square root of 2 with the bracket 311 with the ket P211. This is just, they have different quantum numbers, so it is just 0. And the other case, the other possibility is just 1 over the square root of 3 with the square root of the same term. And this goes with the P311, these spaces are they have the exactly the same quantum numbers. So this is one. And as you may imagine, the other term is just zero. P311 with the P322, this is just zero. So the corresponding probability is 1 over the square root of 9. This is 1 over 3. Now, we have to consider the condition that the problem is telling us that we want to measure the observable when the orbital angular momentum, LC, well, this is when it is an operator, is equal to h bar. In that case, we will have the next possibilities. Those will be when n, L, and m is equal to 2, 1, and 1. And in that case, the operator will behave like something like this. LC operator with the ket 1 and 1. Because why? Because you need to remember the formula LC, L, and M is H, M with the subindex L and M. So with this formula, I don't know. No, it doesn't work. This will be this will be just H with the ket 1 and 1. For the other case, when n, comma, L, and M is 3, 1, 1, we will have the next case. LC will be with the ket 1 and 1, H bar 1, 1. This is the exactly case. Why? Because we are considering just the L and M quantum numbers, L and M, right? And with those quantum numbers, we just use directly this formula, right? The last possibilities when I'm going to write it over here, when N, L, and M is just 3, 2, and 2, in that case, we will have the operator that will behave something like this with the ket 2 and 2. This will be 2 times H bar with 2 and 2. So, for instance, they are asking us, the question says that we need to solve it when we only measure this possibility. And that possibility will be only restricted to these cases. To this case and this case. But as you can see, here, the orbital angular momentum is not what we want. So this case is not available. And when we consider these two constraints, we just need to sum over the probabilities that achieve this. And those probabilities are just when the quantum numbers are 2 and 3. And that will be just 1/2 plus 1 over 3. So the probability will be, yes, I'm going to write it with blue. The probability is of measuring LC equals to H bar will be just 1/2 over 1/3. And this is just the 3 plus 2 over the over 6, 5 over 6. This is this has a sense because this is not greater than 1, so its probability is less than 100%. And thank you for watching. In the future, we are going to solve more problems, and if you understand this, you can subscribe and you can tell us if you don't like something so we can correct it in the future. Thank you. Bye bye.